In this video series, I'll demonstrate how to use ANSYS Fluent's adjoint solver to optimize the shape of an air duct that is packaged within a constricted space, such as you might find within the dashboard of a car. I will optimize the geometry with the goal of improving multiple performance measures that matter to designers, and show how to export the improved design so that it can be converted back into CAD. I'm starting with a case file for which I've already obtained fluid flow results using Fluent's general solver. The baseline design is a simple duct with air flowing from a constant velocity inlet to a pressure outlet. As you can see with this initial design, the total pressure drops as the flow passes through the duct, and the velocity at the outlet is very non-uniform. To begin the shape optimization, I will use the controls in the Design tab. Note that starting in version 18.1, these controls are immediately available for use. In earlier releases, I would have had to first enable the adjoint add-on module using a text command. I will start by defining the observables for which I want to see improvement. My first observable will be the pressure drop, as measured between the inlet and the outlet. The second observable is a measure of the uniformity of the flow at the outlet. This itself will be a combination of three measures of variance in the flow components at the outlet. I'll create volume integral observables for the velocity in each of the coordinate directions, starting with the x direction. I will integrate the velocities within a box that surrounds the outlet, shown here, which is defined by the following coordinates. Now I'll create one for the y direction, and finally, one for the z direction. Having created the individual velocity integrals, I will now combine them into a single compound velocity observable. For the operation type, I'll use a linear combination and I'll select the three components. Combining them requires that I choose their relative weighting up front. In this instance, I'll weight them all evenly with a coefficient of 1. When you have multiple objectives like this, you could proceed by running the adjoint solver for each one. This way offers flexibility since you can easily explore how you would like to weigh their relative importance and blend them to guide the design improvement. Such a process may be preferred for complex problems or when you have competing observables. Alternatively, if you have sufficient insight into the nature of the problem, you can combine multiple observables into a compound observable. This requires that you pick relative weights for the observables before the adjoint solver is run. The benefit is that you will then only need to run the adjoint solver once per design iteration. I'll use the latter method here. To do this, I will linearly combine the flow uniformity observable with the pressure drop into one comprehensive observable. For this combination, picking the relative weighting can require some trial and error. This may involve some experimental runs with different values for weights. I've already performed such experimental runs and found that for this particular case, I can get a balanced improvement in both observables if I make a relative reduction in the pressure drop coefficient. Now I'll select that comprehensive observable as that is the one for which I want the adjoint solver to calculate sensitivity data. I can specify that I plan to minimize this value, so that if I wanted to display contours of the sensitivities, the reported quantities will be properly oriented. I will use the default settings for the solver controls, as the auto-adjust controls work well for a variety of cases. I'll also keep the default monitors for convergence. After I initialize, I can start a run of the adjoint calculations, which in this case may take up to 1,000 iterations. This concludes part 1 of this video series. In part 2, I will use the results of the completed adjoint solver calculation to modify the mesh in such a way as to minimize the observables.